I'm Mark Anderson, and I'm here with Arlene Olivero Sheldon. Our colleague Annalie Barnett could not be here today, but we're going to talk to you briefly about a stream classification system and map and data set that we developed for the Appalachian Landscape Conservation Cooperative. In a short presentation, we're going to go through the goal of the project, the products and the uses of the classification, who is our expert team, the aspects of stream classification that we focused on, and then we combine those variables into stream types. And we're distributing the data and information and report and making it available to you to use. So here's a map of the Appalachian LCC, and our goal was to create a standard freshwater aquatic habitat classification system and a mapped data set that covered that full extent. It's not intended to override any state classifications, but to complement them and serve as a regional classification that links them together so we can look at conservation patterns and freshwater patterns at the scale of the whole Appalachian. The product came out of this are a report where you can read all the details. We'll be going through this in a very high-level overview today, but there's lots of details in the report if you want to know exactly how we created and calculated each variable. There's a GIS stream data set based on the NHD+, and there are some interactive story maps that allow you to use the data. And those products are distributed in two ways, both on the TNC Nature Conservancy Conservation Gateway site, and also on the Appalachian LCC website, and you can go to either one. We hope that the classification would provide common definitions and common ways of mapping aquatic habitats across state lines. It would facilitate a new understanding of aquatic biota on a regional scale and create opportunities to assess the condition of these habitats and prioritize them for conservation action. We hope having a standard regional classification will make for more effective habitat conservation. When we did this project, we assembled a representative steering committee that consisted of 33 stream scientists representing the 12 states in the Appalachian LCC, plus federal scientists. That group participated in bi-monthly calls where we presented information to them and had discussions about the relevance or the correctness of the information, and also pointed the way towards better data sets, or they sent us their own data, or they helped us develop really good, appropriate data sets to create the stream classification from, and reviewed all the final products. Really in debt to this group of 33 scientists, and we have the list at the end of this presentation of all the participants, but they're really helpful in guiding this project and making sure that the results were useful and applicable and hopefully to you. So one of the things we did at first was we went through a long list of classification variables which had been used by the states to classify streams within their state, and then agree upon a set that we thought were really important for classification, that our whole expert team thought. And we could map them at the regional level or at the regional scale with a fair amount of rigor and accuracy. And 6 that we agreed on was stream size, gradient, temperature class, hydrologic class, degree of confinement, and buffering capacity. I'll talk you through the first couple ones of these and then pass this to my colleague Arlene Olivero, who did a lot of this work. So the first was pretty straightforward. Stream size had an effect on the biological assemblages and changes in major ecosystem types as the energy changes with the size of the stream. We mapped 7 size classes and measured the size class based on the size of the upstream watershed or drainage area. F classes range from very small headwaters that had less than 10 square miles in their watershed, all the way up to great rivers that had 25,000 or more square miles in their watershed. And see in this map here the different size classes. And make sure that we had gotten those different size classes, that we had broken size up in a relevant way. We used a threshold indicator taxa analysis to add stream distribution data or fish distribution data and find whether we really had fish that separated or were largely concentrated in one size river or stream or another. So on this graph you can see there were headwater fish species. There were 6 that were really restricted to those very small rivers and creeks, things like creek chub and orange-throated darter. At the other end of this spectrum, there were 7 fish that were really found mostly in those giant rivers, like smallmouth buffalo. And there were groups in between that varied. They varied in their restrictedness, but were concentrated more or less in each size of those 7 river systems. The second variable we focused on was stream gradient, the steepness of the stream, which influences the bed morphology and sediment transport. And we mapped 6 different gradient classes using rise over run times 100 as the measure. So in this map you see here very high, those steep, orange and red colors are very high gradients. And the very low gradients are the more flat, marshy kinds of stream classes you see in the blues and greens and purples. And the stream size, we did a threshold indicator taxa analysis. Again, you can read the details on this in the report to find fish that were associated with one of those gradients. Here, pointing out at the very high gradients, you get almost no fish, but you do get a lot of benthic genera, like certain stoneflies and caddisflies that are really characteristics of those high gradient streams. The low gradient streams, you get into banded fish, or at low gradient, the flathead catfish, emerald shiner, examples of fish. And a lot more fish were characteristic of the lower gradient types than the high gradient types, which had more and more component of benthic species as you got to the higher gradient. Another that we focused on for this piece, we contracted Ryan McManamy from Oak Ridge National Laboratory to develop a hydrologic stream classification based on minimally altered stream reaches and the stream gauges, 428 gauges, I think, that were in the project area. And here we're trying to get a handle on the flow regime and how it sort of shapes the life cycle and reproductive strategies of riverine species. He did principal components analysis to measure the gauges. He had multiple aspects of each stream segment, and he clustered them into stream types that had very similar sets of attributes. And the groups that we came up with that we thought they popped out strongly in the analysis, and we could also map them. And ranged again from stable high base flow, so those are in dark blue on this map, those very high groundwater influenced stream systems. They have low variability. They are consistently, the flow is consistent year round. They have minimum highs and minimum lows, and few severe high flow events. And they rise at slow rates. So they're very stable systems. And you compare that at the other end of the scale on that same row to the perennial, very flashy, the perennial streams that have extremely high variability, high intermittency, high frequency of flows and fast rise rates. So those streams that show a huge amount of variation. And in between, we have them lined up so stable high base flow to perennial runoff that still has high base flow in it, to then perennial runoff with moderate variability, perennial flashy, which has higher variability, to perennial flashy that is the highest variability, all the way to then the intermittent, unpredictable streams, which really do not have mapped very well, but there are a few of them where they just have extremely high variability and are for our purposes, intermittent streams. So logic class. Now I'm going to pass this to Arlene to go through the temperature classes and the rest of the presentation.
Okay, hello. So I'm going to jump in and start with temperature classes that we developed for this project. So as many fisheries biologists would attest to, temperature has a very strong effect on the aquatic species found in a stream or river. It really sets the physiological limits of where our freshwater biota can persist. And we developed a model of stream temperature using actually sample stations of 1,081 least impacted stream reaches. We were to obtain from a variety of state and federal agencies actual temperature logger data. And so to place these known locations into our temperature classes, which were based on the mean summer temperature. And then we developed a model similar to the hydrologic model Mark was explaining, where to really extrapolate and predict for unsampled reaches what their temperature class would be, kind of impacted or unimpacted conditions. So this temperature model, which we again applied to all the stream reaches in the region, explained 80% of the variance in our known temperature data, and we were able to predict these temperatures in the stream reaches using a number of variables, but the most useful ones in the model were really July and August air temperature, and then also some winter flow data. And you get quite a range in this region, from up in the high mountains of New York, Pennsylvania, that have very low summer mean temperature, 16 degrees Celsius, to ones that have greater than 24 degrees. We grouped the continuous temperature data into three major classes. So a cold group, a chill, and a warm group. And similar to previous variables, we ran a thrush indicator taxa analysis, a Titan analysis, to really characterize the patterns of how the fish species composition and abundance changes with temperature. So there were three species that really were found dominantly in the cold class and increased in abundance within that class. That would be things like slimy sculpin, your brook trout, and your brown trout. There were a few species in the transitional temperature class, which ranged from 18 to 22 degrees Celsius. Species here, like your northern hogsucker, your fall fish, your chain pickerel. And we had also a large number of fish species in our warm group that was streams and greater than 22 degrees Celsius throughout the summer. So a lot of fishes, lead horse, spot, minor, and other species. Variable we mapped for the region was confinement, so looking at the degree to which bounding topographic features are really limiting the lateral extent of floodplain development on a river or around a river. And again, it's kind of confinement floodplain really is going to affect the size of the floodplain, but also if the channel of the river can meander and move over time, it affects flood dynamics, the riparian habitats, water quality, sediment regime, different biochemical cycling. So this is an important variable and something new that we really added to this classification that hasn't been able to be mapped in a lot of stream classifications before. And we were able to do it using a river confinement model that we developed with a 10-meter DEM. So we mapped and modeled a floodplain along all the streams and rivers in the region, and then we compared the width of the floodplain to the width expect the stream or river to be at bankful condition. So we took again our continuous confinement data, and we summarized it for stream or river into 3 categories. So was the stream or river confined, confined, or unconfined? And you can see in here the confined streams and rivers more red or pink, moderately confined in the greens, and then the unconfined rivers that can really meander a lot and have a wide floodplain in comparison to stream width. Those are in blue. And lastly, the last variable we mapped and modeled for all the streams and rivers was buffering capacity. And this particular attribute of streams really protects against rapid ranges in pH. Most aquatic organisms need the water pH to be within 6.58 on the scale for really optimal growth and reproduction. And again, used known sample data, almost 1,600 here, least impacted beaches. We knew the alkalinity on the ground, and then out to unknown locations using a random forest predictive model that explained very much of the variance, and was really keyed in on our geologic map that we had compiled. It really, this particular model, particularly the percent calcareous bedrock geology in the upstream watershed to place the streams and reaches into a very category, which you see in the blue, a high category green, a moderate category in orange, and then your low volume, more like the acidic streams in red there. And, we did again a special indicator tax analysis to characterize the fish and the benthic species by alkalinity class, and again found some patterns where certain species are preferring your well-covered, more alkaline settings versus species preferring your more acidic, your low alkalinity settings. So you see just a sampling of some of the species, the low species, like the rosy side dace, up to these that prefer found in our highly alkaline settings, species at the other end of high alkalinity species like creek shore, black-side darter. So again, we felt that all these variables were important to characterizing the ecological habitat found in the streams and rivers. We simplify how we integrated these variables into the major types of streams and rivers, the end project. I want to share with you just a little bit about that now. So we had our core 6 variables, and then we decided to integrate them by for headwaters, using different rules for headwaters and streams versus the medium to great rivers. And the difference is for the headwaters and the small rivers, the team preferred and felt gradient was a more key sharing variable to the habitat and the biota, whereas for the medium to great rivers, the team felt that really confinement of the floodplain rather than the actual reach gradient was the more important variable structuring the ecological community. So you can see from this how we combine variables, the size, gradient, the temperature, and the hydrologic class, for the headwaters and small rivers, and then the combined with the temperature and the hydrants for the great rivers. And an example of one of the types that emerged from this would be like here, high gradient, cold, headwater, low gradient, or a low gradient, unconfined river. So there were 62 of these combined types in the region, and you can look at patterns in how they're distributed across the analysis area. So for stream rivers, for example, this common type was our warm, medium gradient, flashy headwater or creek. And second most common type was a cool, medium gradient, perennial flashy headwater system. So the data, you can look in your own particular state or watershed and see the distribution of these types and compare the characteristics of your watershed, for example, to the characteristics of the larger state or region where you're doing work. For rivers, the most common types of small rivers were warm, low gradient, perennial flashy rivers. And then into the medium rivers, they became more commonly unconfined, so warm, unconfined, perennial runoff medium rivers, and similar, our largest class of rivers had warm, unconfined, perennial runoff large rivers. And you see the pattern here of how they're both by temperature and confinement at the hydro class in the little inset map. In addition to the 62 combined types that came out of this project, the data is also coded with the regional stratification that the streams and rivers are in. And we included 4 different stratifications, freshwater ecoregions, which you see here in the left, fresh ecoregions, we include them here, and then some kind of scale units, these freshwater eco-drainage units, which are nested within freshwater ecoregion, actually, and these water-based units that a lot of the states are using in their management. We did code those as part of the classification, but you can see for any reach what stratification it's in and easily and quickly pull out all in a particular freshwater ecoregion or eco-drainage. So we hope these results will be useful to the managers and conservation planners in the region. We hope it will be able to investigate ecological relationships and inform better conservation planning for aquatic biodiversity across the region. We encourage you to explore data through the web maps and download the data and report. There's a couple of places where you can get the data. It's being distributed on the Appalachian LCC website, which you see here. You can get the data. Also have a little story map where you can view each topic and the maps that were in the report. You can zoom here. You can't really zoom in on them, but you can view them here. The data being distributed on our Nature Conservancy website, so you can go to the page to get the classification of the data, and actually worked up a map which we're pretty excited about and have just released. It lets each one of the core application variables and any one of them, and it also lets you look at the combined 62 type classification. So again, zoom in, you can on a particular reach, and you'll get a pop-up of the attributes of that reach. So if there's a particular planet, you can easily and pretty quickly get to it and see what stream or river we've mapped it and what type, what class it would fall into. And labels come on, and there's a few other features. We encourage you to just get it the web map and start exploring the data. So again, we want to thank you for especially especially thank the organizations and the many individuals who contributed to this project, especially the Appalachian LCC, who envisioned the project and provided the funds to really make it a reality. And then people who contributed dates and time. John Pastuni at the Wildlife Service, Ryan McMay, who worked at Geologic Classification, Dylan Harris, University of Brad, who helped us a lot with the confinement models, Darren Cuddle of USGS provided temperature data, of Michigan State and provided temperature data, and helped the record go on. He provided temperature data as well. So again, everyone who participated, and especially also the 34 members of our steering committee. More to Mark?
Oh, thank you very much. We hope you find it useful, and please let us know if it's helpful, how you're using it, or if you find something you think we fix, or let us know, and we'd be glad to hear from you.